One of the final molecules on the list is molecule X or sample X, and we're going to determine now what sample X is. When we submit sample X for the unsaturation test, the orange colour remains, and this means that we don't have any carbon-carbon double or triple bonds, so we don't have an alkene or alkyne functional group. When we do the oxidation test, the orange colour remains, so this means that we don't have any oxidation. So we can say that we probably don't have any primary or secondary alcohols or an aldehyde functional group. And finally, when we do the carboxylic acid test, we don't end up with any bubbles, which means there are no carboxylic acid functional groups in our molecule. Looking at the IR, again from about 1500 downwards, I don't really worry about that region. It's the fingerprint region. It doesn't give us a lot of different details. So from 1500 up, I start to look for important signals. Something that jumps out at me right away is this signal here. So we have two little peaks, which at this point I wouldn't worry too much about. I would just look at where this signal is coming. Don't worry about if it's two separate signals. So it's about 1650, and this is where we would expect to see a carbonyl group. So we can go ahead and draw that in as a potential functional group. Then we move down our spectrum, seeing nothing around here. Hitting around 2900 is where we see our CH stretching or vibrations. And that we see in almost all molecules, unless your molecule doesn't have a carbon-hydrogen bond. But at this stage, that's very unlikely. And then we hit this area of our molecule here. And here we do really see two quite different signals coming from around the same area. So this is about maybe 3200 to 3400. It's not broad like we would expect in a water signal. So water signals, remember, OH alcohol signals are usually quite broad, and then you don't pick out any definite peaks. So this is probably a signal belonging to an amine. Now from here you can start making some suppositions, thinking about what you want to test, what functional groups might be in your molecule. Given that we have an amine and a carbonyl group, are we dealing with a carbonyl group and a separate amine? So are we dealing with a ketone and an amine? Could we possibly have an ester and an amine? Or could we have an amide? Are these two signals close to each other? Something to keep in your head as we go through. The next thing I do is check the carbon NMR to see how many carbons we have in our molecule. And remember, this doesn't work if you have a symmetrical molecule, so it's just a guide. We have 1, 2, 3, 4, 5 carbon signals. And we'll have a look at what this signal might be a little bit later. Now it's just thinking about generating our molecular formula. For the proton NMR, we have 2, 4, 6, 8, 11 protons or hydrogens. So if we take into account these 5 carbons, 10 hydrogens, 1 oxygen and 1 nitrogen, we do end up with our molecular mass of 101. So this would be our molecular formula, remembering this is 11. Coming back to our carbon NMR, the area I'm most interested in is this signal here, which is between 160 and 180. And this is indicative of a carbonyl carbon that belongs to either an ester or an acid. Now, we know we don't have an ester because we don't have 2 oxygens, and we know we don't have an acid because we don't have 2. When we did the acid test, we didn't see a signal. But we are in this region of esters and acids, and we're not in the region of aldehydes or ketones. So we probably don't have a ketone and an amine. We probably could work on the assumption that we may have an amide. to sort of make it a little bit more targeted in our next steps. Don't discount having a ketone and an amine, but our NMR spectrum signal is suggesting this isn't the case. Now, the last thing we look at is the NMR spectrum. And before I do anything at looking at this spectrum, I want to draw in what I think is the start of my molecule. So I know I have 5 carbons. So I'll draw those down first. And don't forget I have a nitrogen somewhere. The next thing I do is look at the very end of my spectrum, 0 to 1. And I'm looking always for this signal here because it's a really easy signal to pick up. It integrates for 3 and is a triplet. So it's probably a CH3 group next to a CH2 group, next to 2 other protons. And this is something I can put in straight away to my molecule. That should be a 3 there. Then I move down the spectrum and I have a look at my next signal, which is for integrating for 2 hydrogens. So that would be a CH2 group. And it has 1, 2, 3, 4, 5, 6 signals. So it's a sextet, which means it's next to 5 hydrogens. My next signal is also for 2 hydrogens, so a CH2 group, and it is a quintet. So it will be next to 4 hydrogens to give it that splitting pattern. And then my final signal is another CH2 group, but it's a triplet. So it is probably next to another 2 hydrogens. Then my final signal out here corresponds to 2 hydrogens. But can you see it's a singlet and it's a bit broad? And this is a bit like our OH signal. When we see a broad signal, it's usually due to the OH or NH protons. In this case, it will be due to our NH protons. They are also displaceable. They can pop on and off in the deuterated solvent. And we have 2 of those, which means that our amine is probably on the end of our molecule. And how do I know it's on the end of our molecule? Well, nitrogen forms 3 bonds. If it's at the end of our molecule, 2 of those bonds can be to protons or hydrogens. If it's in the middle of our molecule, we'll only have 1 proton. So this means my nitrogen is sitting at the end of my molecule. Now we probably have an amide, which means we have a terminal amide. Later on, we'll check to make sure that the carbonyl group, for instance, isn't sitting in the middle of the molecule. But at this stage, we're going to hypothesize that we have a terminal amide. And that means that my other CH2 groups will be here. Now it looks like we finished our molecule, but we always do a double check. Starting at this end, our CH3 group is next to 2 other protons, so it should give a signal that's a triplet and integrates for 3. Because it's not next to any electronegative elements, it's going to be fairly upfield, which is what we see, sitting at about 0.9. Our next signal is this sextet, and it's a CH2 group next to 5 other protons. So we look at our 3 CH2 groups and we say which of them are next to 5 other protons. It will be this CH2 group here, which is next to 3 protons plus 2. So this would be signal number 2. And again, it's pretty upfield because it's not really next to anything electronegative. Then we move to our next CH2 signal, which is next to 4 other protons. So we would expect this signal to be a quintet. And we move to our final CH2 signal, which is next to this carbonyl carbon, so it will be shifted up downfield, and it's next to 2 other protons, so it should be a triplet, which gives us this signal here. Finally, we have our 2 proton signals attached to our our nitrogen as part of our amide. And this gives us our final molecule. Now we need to give it a name. It is an amide. We have 5 carbons, so the final name for our molecule would be pentamide. Or pentanamide, however you want to pronounce it. Pentanamide is probably the most correct way of saying it. So just as a thought experiment, if our amide was not a terminal amide and was internal, so in the middle of this carbon chain, how could we make sure we hadn't misidentified it? So a couple of different examples. We have pentanamide, which is this spectrum here that we just looked at. But what if we had methylbutanamide? So we had our methyl group here and only one amine nitrogen. That would mean that this signal here should integrate for 1, and I would expect to see a singlet integrating for 3 somewhere upfield. So maybe we wouldn't get super high, but somewhere upfield as a singlet. I would still expect to see my triplet here for my 3 hydrogens. I would still expect to see this signal here, my triplet for my 2 hydrogens. And then somewhere in here, I would only see the sextet. If we were looking at ethyl propanamide, again, I would only see 1 hydrogen up here. And then I would expect to see somewhere a little bit higher, a triplet integrating for 2, which would be these 2 hydrogens here. I would expect, sorry, not a triplet, I mean a quartet. Let me erase that and draw the right one. So quartet somewhere up here. I would still expect to see this triplet maybe moved a little bit downfield. And then here I would expect to see another quartet somewhere here. And then I would expect these to become another triplet integrating for 3. Something like that. So you can always think about, have I got the right molecule? Have I got the right connection of atoms in the right order? By thinking about, what if I had this? How would my NMR spectrum look different? So that's just another check you can do to make sure you're on the right track. This is my last molecule to go through, helping explain for you. I hope you found these series of videos helpful, and hopefully they've given you a few more tools in your toolbox for structure determination.